Welcome. In this session, we'll explore a convex function and we'll generalize from the scalar case to a vector case. Let's recall a convex function. And that said that if we have a value u and a value v that are in an interval where this is defined, if we take a step theta away from u and towards v, that is, if we take 1 minus theta times u and add theta times v, that will step us when theta equals 0, this will equal u. When theta equals 1, this will equal v. And if we evaluate the function at that interpolated scalar value, that the level of the function is less than or equal to the interpolation of the level. And that is, if we evaluate the function at the argument u, and we evaluate the function at the argument v, and then we perform a linear interpolation of this, which is we take 1 minus theta times the level at u and add theta times the level at v, that this is always at least as large as the level at the interpolant. So that is a convex function of a scalar argument. So for a function that has a vector argument, it turns out that this is a really direct generalization. What we do is we have a vector u and a vector v, and we use the same reasoning as before. And that is that if we linearly interpolate between these vectors, and we evaluate at that interpolated vector, that is less than or equal to the result of doing the linear interpolation of the levels. And so if we evaluate the function at the argument u, and we evaluate the function at the argument v, and then we linearly interpolate, that this interpolated value is always at least as big as the value of the interpolant. So example is an affine map. And an affine map is a slight variation on a linear map. So let's suppose that we have function 1 that has a vector argument, and that this is some one form 1 times the argument plus some constant. So this isn't linear, because if we multiply w by 2, for example, there's no guarantee that f1 is doubled. And we might have another function. So imagine we have function 2, and it is also an affine map. So it is some possibly different one form plus c2. Now let's take some concrete examples. Suppose we set one form 1 to be minus 1, 1, and let's say that our constant offset is minus 2. And now suppose we have one form 2, and this is 1, 1, and now our constant offset is plus 2. So it's easy to verify that these are convex functions. That is, if we take these interpolation rules and we apply them, it's easy to show they're convex. It's also, this would be a good idea. Can you show that they are not strictly convex? Because that'll help you understand the difference between convex and non-convex. So while you're thinking that through, let's switch to some computer-generated examples. Now, let's take a look at some examples. So when we use MATLAB to visualize these, what we can do is we can use the mesh function, and the mesh function will let us take this first affine map and it'll let us plot it, and we see that the affine map produces a plane. And if we really investigate deeply, what we'll discover is that that one form is the transpose of the normal vector for the plane, and the constant represents a vertical offset of that plane. Similarly, for the function 2, we have a different normal vector, and so it's got a different orientation, and it has a different offset. Now, the answer to that previous problem was that that inequality for an affine map is an equality. So it's convex, but it's not strictly convex. Now, let's take a look at a quadratic form. So a simple quadratic form is the simplest possible, is where we take the vector argument and we multiply it with its transpose. And we could put a symmetric positive semi-definite matrix in here, but for now we'll treat it as the identity and we'll just eliminate it. So in general, when this is a symmetric positive semi-definite matrix, it has this form. So let's take a look at these two functions. Let's take a look at this one, which is the level of a function is the square of the vector norm of the argument, and in this it's a weighted sum. You can verify that these are convex functions. So now the surface meshes look like this. What we see is for the first function, where the level is the squared norm of the argument, this is a paraboloid and it's a surface of revolution. For the other one, it's a different shape. So this is also a paraboloid, but it's no longer rotationally symmetric. It's sort of squished in one direction and stretched out in another. And those are the effects that are caused by those diagonal entries of the matrix that we just looked at. So both of these are referred to as elliptic paraboloids. This is a circular paraboloid and this is a strictly elliptic paraboloid.